The story begins in 1905 when Albert Einstein unveiled his groundbreaking explanation of the photoelectron effect, and this phenomenon, which occurs when light shines on a material and electrons are emitted, sparked a revolution in physics. Einstein's work on the photoelectron effect earned him the Nobel Prize in Physics in 1921. Einstein's discoveries laid the foundation for the development of the concept of the photon, the quantum of electromagnetic energy, and this quantum particle of light plays a crucial role in photoelectron spectroscopy. Spectroscopy, in general, explores the matter using the various parts of the electromagnetic spectrum, but photoelectron spectroscopy takes a unique approach using the photons to interact with the electrons. Ultraviolet and X-ray wavelengths are particularly common in photoelectron spectroscopy as they offer valuable insight into the matter under scrutiny. In fact, photoelectron spectroscopy is sometimes referred to as photoemission spectroscopy because it relies on the energy emitted by electrons when they interact with photons. So, by measuring the energy of the emitted electrons, we can gather crucial information about the material's properties and electronic structure.
That's just remarkable, Azyan, to think of using electrons to study materials. An electron is so minute and fundamental to our surrounding environment. Yet, with the aid of photonic energy, an electron is capable of bringing out the essence in everyday material so that we may study, analyze, and perhaps optimize for better functionality. Photoelectron spectroscopy employs many kinds of wavelengths from the electromagnetic spectrum. Today, let's look at how it uses ultraviolet as well as X-ray wavelengths of the electromagnetic spectrum. With Einstein's publication setting the groundwork for subsequent developments in 1905, P.D. Innes documented the first ever photoelectron spectrum of X-rays. He'd attempted this with photographic plates, a magnetic field hemisphere, a Röntgen tube, as well as Helmholtz coils. He recorded broad bands of emitted electrons as a function of velocity. Once additional details were added by other researchers on the broad bands, the development of a prototype began. XPS gained more recognition after the Second World War thanks to Kai Sigban, who improved the equipment used before. It allowed him to document the first high-energy resolution XPS spectrum of cleaved sodium chloride in 1954. What resulted from this gave Sigban the ability to identify elements and the elements that were bonded to them in a multi-elemental composition. In 1969, 3 engineers from Hewlett-Packard teamed up with Sigban and successfully invented the first commercial monochromatic XPS instrument, leading not just to Sigban earning himself a Nobel Prize in 1981, but to extensive analysis into a multitude of materials. It wasn't until 1957 that Sigban's prototype began operations. This became the foundation for his paper on electron spectroscopy for chemical analysis. So, what is XPS exactly? It's a surface-sensitive and non-destructive technique of analyzing the outermost layer of atomic structures. Usually for layers as thick as 10 nanometers, the instrument sends X-ray photons towards a target material, allowing one to observe the energized surface electrons' behavior as well as properties. More specifically, XPS is useful in determining 3 key quantities. Besides insight into the behavior, properties, and structure of materials, studying elemental composition provides useful information on the presence of impurities on material surfaces, which sheds light on potential surface defects and disruptions in the material's optimal functions. XPS measures relative abundances of material surfaces, providing information in the form of peaks over varying energies. This is especially useful in studying the effect of elemental composition on the surface material behavior. It allows researchers to further develop and optimize the designs of future materials that function more efficiently. Chemical states are an essential component to material interactions. The oxidation states of polyvalent ions, in this case, determines their affinity to lose or gain electrons, and hence the resulting effects on the material surface when those changes take place. XPS studies chemical states by analyzing the binding energy peaks corresponding to them of the polyvalent ions in the sample. These energies are outputs produced by photoelectronic signals originating from core level electrons ejected by X-ray emissions. Ultraviolet photoelectron spectroscopy uses the same principles as XPS. The major difference here is in the energies of its ionizing radiation used to induce the photoelectric effect. Unlike aluminium and magnesium used in XPS, UPS utilizes a helium gas lamp instead, where the emitted photons are at different energy levels. In St. Petersburg State University of Leningrad, there came the pioneering of UPS to study the photoelectron spectra of free molecules in the gas phase. Here, the measurement of photoelectron energies was made with an analyzer while radiating monochromatized hydrogen onto the material. The year after that, English chemist David Turner made further developments by employing a helium discharge lamp as a source of photons. This time, the photons emitted a wavelength and a corresponding energy which allowed them to obtain an energy resolution of 0.02 electron volts. The Nebraska Center for Materials and Nanoscience describes UPS as a means capable of measuring 3 key quantities of the material with high precision: the Fermi edge, the density of states, and the electronic work function. The Fermi edge and work function are, simply put, energies that interact with the electron in a manner opposite to one another. The density of states is a key aspect of material characterization, importantly in determining a material's conductive property, and hence what kind of material it is. For instance, a material with high density of states indicates a large amount of available energy states in a certain energy range for electrons to occupy. Electrons can transition more easily between different states, leading to higher conductivity. This is a characteristic feature of metals, that they are good conductors of electricity. A material with low density of states, on the other hand, means that there aren't many states in the energy range for electrons to occupy, making it harder for them to move. Intuitively, the material has a low conductivity and, in comparison, is considered an insulator. Semiconductors lie in between these two types due to their moderate density of states. So what runs behind all this state-of-the-art equipment? It's the application of the photoelectric effect. Einstein did make a prediction. An electron would be emitted from an atom in response to impinging electromagnetic radiation. Here, it is to say that electrons excited by light would be released from the surface of a material when the energy of the incident photons from light exceeds the binding energy of that electron bound to the material surface. Here, the energy needed to release the electron is proportional to the frequency of the incident photon and not the exposure time or the intensity of the photon itself. The motion of ejected electrons from a material surface is associated with their kinetic energy, which is also linked to the binding energy of each electron. Because atoms themselves have multiple orbitals of electrons with different energy states, the excitation of electrons from surface atoms will result in a range of varying energy levels, hence an energy spectrum that is displayed from a spectroscope.
Photoelectron spectroscopy is incredibly important because it helps scientists in explore the properties of different kinds of matter such as solid, gas, and liquid. It does this by measuring the energy levels of electrons in their orbits around the atoms. And by studying these energy levels, scientists can gather the information about the elements present in a material and even learn about the bonds between the atoms. Photoelectron spectroscopy is highly accurate and reliable when it comes to the measuring these electron energies, making it a valuable technique in scientific research. It allows us to understand and fundamental characteristics of materials in a precise and detailed way. The application of photoelectron spectroscopy are vast benefits such as geology, biochemistry, and material science. In medical research, it verifies the presence of antibacterial silver in wound dressing. In energy storage, it helps us understand the degradation of solar cells, and in basic chemistry, it unveils the secrets of phase transition and crystal nucleation. Photoelectron spectroscopy is known for its accuracy and reliability in measuring the electron energies. It provides scientists with a precise and detailed understanding of the fundamental characteristics of materials. Thanks to photoelectron spectroscopy, scientists can unlock the hidden mysteries of matter, revealing its elemental composition and shedding light on the intricate bonds that hold it together.
Photoelectron spectroscopy,
A remarkable tool
illuminating the secrets of our world.